Okay, so we have the second part of section 11.6 today, talking about in particular the gradient vector. And by the end of the day, we should be able to calculate this gradient vector associated with the multivariable function. And we should be able to use the gradient vector to determine the direction in which a function achieves the largest possible rate of change, as well calculate that actual maximum rate of change. And finally, we should be able to determine the direction of a gradient vector from a function's contour map. Okay, let's get started by defining this term. The gradient of a function f of x, y, is this function that came up, this vector that came up when we defined the directional derivative yesterday. It's the vector that has f sub x as its first component and f sub y as its second component. So if we wanted to rewrite the directional derivative in terms of the gradient, then we can do that. Now, the gradient is traditionally represented in one of two ways. It's represented either by the letters grad next to the name of the function f, or sometimes I will also see this upside down triangle symbol, and this symbol is called nabla. Is called nabla. So this is typically read as grad f, and sometimes it is denoted with this upside down triangle symbol called nabla. So if I wanted to express the formula for the directional derivative in an alternative way, one way that we could do that is we could say the directional derivative is equal to the gradient vector nabla f grad f dot product with u. Okay, now here begins a portion of your math journey where vector quantities will not reliably be indicated by these arrows here. There are some things that you're just going to have to remember are vectors, even though you don't see the vector arrow. And the gradient is one of those things. The gradient of f, this quantity, is a vector, even though I pretty much never see it represented with a vector arrow or vector bar over top of it. You're really just expected to know that it is a vector. And we will encounter many more situations like that as the course progresses, where there are quantities which are not noted to be vectors. You're expected to remember that they are vectors. And this is the first one of those. Okay. Now the gradient is a very special vector indeed. The gradient, as we explored in yesterday's concept check, is related to the function's largest possible rate of change, because the gradient vector is, if we set, this is a thought level, if we set u equal to the gradient of f, then the angle between these two vectors is 0, so cosine of the angle between them is maximized, so the dot product is maximized. So if you want your rate of change to be as fast as you possibly can, all the possible directions of movement, you want to increase f as fast as possible. Move in the direction of the gradient. That's our first point. The gradient is the direction that will lead to the maximum, the largest possible increase in the value of your function f. If you move in the direction of the gradient, you will increase the value as fast as possible. Not only that, the magnitude of the gradient vector This will tell you how fast the function is actually changing when you move in the direction of the gradient. Is the function's actual maximum rate of change. So just be a little bit careful. The gradient itself, this vector, is the direction that you should go to achieve, to get the maximum rate of change. But the rate at which you're actually changing, which is so big and nice, is given by the magnitude of the gradient vector, is the maximum rate of change. One is the direction, one is the rate. Okay, now what if you wanted to decrease the rate of change as much as possible? What if you wanted to decrease the value of your function as much as you possibly could? The negative of the gradient negative nabla f will cause f of xy to decrease at the maximum rate. So if you want to decrease f as fast as you possibly can, there's some kind of emergency, you need to get that value down right now, find the gradient of your function and take the negative of that gradient, and that's the direction that you should go in to decrease the function's value as fast as you possibly can. So let's do a quick concrete example here for this function f of xy equals 4x squared y plus y to the 5th power. Let's determine the direction of maximum rate of change at the point 2, -1. Then let's determine the actual maximum rate of change at that point. So to begin with, we need to find the gradient, which is the direction of maximum rate of change. And in order to find the gradient, we need to find the partial derivatives. So let's start there. The partial derivative in the x direction, take the partial derivative with respect to x, and we get 8xy plus 0, because the y term vanishes. And we get f sub y. Applying the power rule, we get 4x squared plus 5y to the 4th power. And if we plug in the given point, to -1, then from the x derivative, we get 2 times 8 times -1, which is -16. And from the y derivative, we get 2 minus 1, which is 4 times 2 squared, plus 5 times -1 to the 4th power, which is 16 plus 5, which is 21. Alright, so based on that, our gradient vector has this -16 for the x component and 21 for the y component. And this is the direction that we should go from the point 2, -1 to increase the value of the function as fast as we possibly can. So then someone says, all right, that's the direction we should go to increase the value as fast as we possibly can, but how fast will the value actually go up? The maximum rate of change can be found by taking the magnitude of the gradient vector, which is the square root of 16 squared, x coordinate squared, plus 21 squared. Now I'm not going to bother to try and calculate that just sitting here right now, but with some arithmetic, you will get the value of this quantity, and then you will be able to report your final answer. This number, whatever it happens to be, is the maximum rate of change. Alright, so the direction of the maximum rate of change is given by the gradient. The magnitude of the gradient tells you how fast the function's value is going up. Okay, so now let's consider what happens if we try and find some gradients using contour maps. So on the contour map of f of xy given below, sketch the gradient vector at the point -2, -1, and again at the point -1, 0. Point -1, comma, -1, which as before is located on the level curve right here. And so let's go ahead and consider what we would get if we traveled a little bit, trying to increase the output of the function as fast as possible. Now, let's think about this. First of all, if I want to increase the value of the function, I'm going to have to be moving toward the green level curve here, because that green level curve, z equals -1, will be larger than what I have right now. Now, the question is, amongst all of these vectors, in the direction of the green level curve, which will cause z to increase, which one will cause z to increase as quickly as possible? And so we'll use another guiding principle to help us do that. We saw that du of f is equal to 0 when u is tangent / if you prefer parallel to a level curve. If you want to get as far away from 0 as you possibly can, if you want this quantity to be as large as it possibly can get, then you need u to be as far from parallel as possible. And the furthest away from parallel is what we call perpendicular. It is maximized, if I can spell maximized, when u is perpendicular. Oh, the spelling's gone downhill, hasn't it? Perpendicular to a level curve. Now, if the derivative is maximized when u is perpendicular to a level curve, and the derivative is maximized when u is equal to the gradient vector, then it must be true that that the gradient vector is perpendicular to a level curve. So let's go back to the point -1, -1, and then let's consider drawing the gradient vector so that, first of all, it's pointing in the positive direction towards z equals 1, but also we need to draw it so that it is perpendicular to the level curve. And so the blue vector that I have drawn on this image, on this contour map, satisfies both conditions. It is increasing as fast as possible because it is getting away from its current level curve as fast as it possibly can. And it is in the positive direction because it's pointing toward a higher z value. All right, let's try it again with the point -1, 0, which I will draw right here. Now, as before, the gradient vector points perpendicular to the level curve that you're sitting on. It could point either to the left or to the right. But if I go to the left, the z value will decrease. Only if I go to the right will I move from z equals -1 to z equals 0. So that means that the gradient vector at that point must point exactly to the right. Perpendicular to the level curve in a direction which causes the z values to go up. So that is how we draw and find gradient vectors from these contour maps. Draw them perpendicular to a level curve in a direction so that z is increasing.